The periodic table of the elements, or simply the periodic table, is a tabular arrangement of chemical elements. It is a very handy tool in analyzing chemical elements and their compounds from many aspects, and no wonder it is widely used in chemistry and also other branches of physical sciences like nuclear physics. The periodic table helps us to consider all chemical elements together or as a whole. It provides us with a very useful framework in which properties of elements, sometimes very similar, sometimes very different, can be related or compared with each other, and notably recurring pattern or periodicity of properties can be represented. The first recognizable periodic table has been attributed to the Russian chemist Dmitry Mendeleev, where many other scientists had also made great contributions to the concept of the periodic table before or after him. Mendeleev published his first work in 1869 and a second improved version in 1871. Mendeleev in his work generally arranged elements according to their atomic weights, but also paid attention to their chemical properties like their valencies. Mendeleev's work well exhibited periodicity of chemical properties of elements, where he summarized such behavior as the periodic law by stating when arranged according to their atomic weight, elements exhibit an apparent periodicity of properties, or in other words, a periodic recurrence of similar properties. From Mendeleev's time to our time, due to discovery or synthesis of new elements and also advancement of practical and theoretical knowledge about elements, the periodic table has been changed and improved widely. Our modern periodic table includes 118 approved elements which are listed in the order of increasing atomic number instead of atomic weight. In the common or standard form of the periodic table, each element has its own specific box or square in which information about that element, like its atomic number, symbol, name, and atomic weight, are contained, and the periodic table is a tabular arrangement of these boxes. It is composed of horizontal rows called periods and vertical columns called groups, where atomic number increases from left to right in the rows or periods and from top to bottom in the columns or groups. The underlying basis of this arrangement is electronic configuration of atoms of elements, or in other words, the distribution of the electrons of atoms over a set of atomic orbitals. As it was mentioned, the horizontal rows of the periodic table are called periods. The common form of the periodic table consists of 7 complete periods. The first period, or the period 1, containing only 2 elements, hydrogen with atomic number 1 and helium with atomic number 2. The second period, or the period 2, containing 8 elements, from lithium with atomic number 3 to neon with atomic number 10. The third period, or the period 3, containing 8 elements, from sodium with atomic number 11 to argon with atomic number 18. The fourth period, or the period 4, containing 18 elements, from potassium with atomic number 19 to krypton with atomic number 36. The fifth period, or the period 5, containing 18 elements, from rubidium with atomic number 37 to xenon with atomic number 54. The sixth period, or the period 6, containing 32 elements from cesium with atomic number 55 to radon with atomic number 86. The seventh period, or the period 7, containing 32 elements from francium with atomic number 87 to oganesson with atomic number 118. The two rows at the bottom of the periodic table in fact belong to locations after barium and radium in 6th and 7th periods as their original places. However, since their inclusions in 6th and 7th periods will result in a very long 32 column and hard to represent format for the periodic table, it is preferred that these two rows are represented separately at the bottom, with this fact in mind that there are parts of periods 6 and 7 and not different periods in their own. As it was mentioned before, the vertical columns of the periodic table are called groups. They are also known as families. The groups of elements in the periodic table are numbered from 1 to 18, where the number of each group corresponds to the position of its vertical column from the left side of the periodic table. Again, two separate rows at the bottom of the periodic table are treated differently and no group number has been assigned to them. Although there are debates on consideration of either lanthanum and actinium or lutetium and lawrencium as additional elements of group 3. Each group can also be named from its top or first element. For example, the group 13 or the boron group contains elements boron, aluminium, gallium, indium, thallium, and nihonium. So, with the exception of separate elements at the bottom of the periodic table, the location of each element in the periodic table can be specified exactly by its period number and group number. For example, the element iodine with atomic number 53 is located at the period 5 and group 17. In the case of separate elements at the bottom of the periodic table, we can only specify the period number and not any group number. Whereas discussed before, elements from lanthanum with atomic number 57 to lutetium with atomic number 71 belong to the 6th period, while elements from actinium with atomic number 89 to lawrencium with atomic number 103 belong to the 7th period. Also, it should again be noted that in period 6, either lanthanum or lutetium, and in period 7, either actinium or lawrencium are proposed as candidates for group 3 elements of periods 6 and 7. However, until now, there have been no agreement on this, and currently, due to similarities of properties, for two separate rows at the bottom of the periodic table, 15 elements of each row are considered together and none has been moved to the position as a group 3 element. In addition to periods and groups, we can also talk of blocks of the periodic table. Each block corresponds with filling of one type of atomic orbitals. There are 4 s, p, d, and f blocks corresponding with filling of s, p, d, and f atomic orbitals respectively. The s-block elements are elements of groups 1 and 2 plus helium from group 18. The p block elements are elements of groups 13 to 18 with the exception of helium. The d block elements are elements of groups 3 to 12. Finally, the F block elements are separate elements at the bottom of the periodic table where elements of the first row of the F block or elements from lanthanum with atomic number 57 to lutetium with atomic number 71 are called lanthanoids, while elements of the second row of the F block or elements from actinium with atomic number 89 to lawrencium with atomic number 103 are called actinoids. Here it should be noted that lanthanoid and actinoid are preferred to previously use lanthanide and actinide. Also, it should be noted that based on electronic configuration and capacity of atomic subshells, each row of the block F should contain 14 and not 15 elements. And in fact, one element from each row of current F block belongs to the block D, where there is debate on choosing either the element at the beginning of each row or the element at the end of it as the D block element, and currently, due to similarities of properties, 15 elements of each row are considered together. There are more terminology to follow. The main group elements, also called representative elements, are elements of blocks S and P, or equivalently elements of groups 1, 2, and 13 to 18. Except in group 18, the first two elements of each main group are termed typical elements. The transition elements are elements of the D block, or equivalently elements of groups 3 to 12, where it should be noted that there is debate on consideration of elements of group 12 and sometimes group 3 as transition elements, and based on similarities between properties, some prefer to consider group 12 elements and sometimes group 3 elements as main group elements. Finally, in a transition elements are elements of block F, or lanthanoids and actinoids together. There also exist other IUPAC approved collective names for like elements. Alkali metals are metals of group 1, or all elements of group 1 except hydrogen. So lithium, sodium, potassium, rubidium, cesium, and francium are alkali metals. Alkaline earth metals are elements of group 2, which are beryllium, magnesium, calcium, strontium, barium, and radium. Pnictogens are elements of group 15, which are nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. Chalcogens are elements of group 16, which are oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Halogens are elements of group 17, which are fluorine, chlorine, bromine, iodine, astatine, and tennessine. Noble gases are elements of group 18, which are helium, neon, argon, krypton, xenon, radon, and oganesson. It should be noted that all elements of period 7 are radioactive, and especially elements at the end of the 7th period, like moscovium, are very short-lived radioactive elements with unknown chemical properties. So it is customary to not include them in discussions. Another IUPAC approved collective name is rare earth metals, which are scandium, yttrium, and lanthanoids, where scandium and yttrium are from group 3. We discussed how groups are numbered from 1 to 18. This is the modern group number system which has been recommended by International Union of Pure and Applied Chemistry or IUPAC since about 1990. Two earlier group number systems exist. One was used by the Chemical Abstract Service or CAS, where the CAS group number system was more popular in the US. The other one was used by IUPAC before 1990, where this old IUPAC group number system was more popular in Europe. These two earlier systems used number letter designations instead of just numbers. Both of these number letter designations generally consist of one numeral, either Arabic or Roman from 1 to 8, and one of the two letters A or B. Both systems generally use same numerals for groups, where these numerals roughly correspond with the highest oxidation number of the elements in that group. But two systems differ in using the letters A and B. The CAS group number system assigns A for the main group elements and B for transition elements, while the old IUPAC group number system uses A for the left side of the periodic table and B for its right side. For example, the group 14 in the modern IUPAC system is the group 3A in the CAS system and the group 3B in the old IUPAC system. In addition, both CAS and old IUPAC systems consider groups 8, 9, and 10 as one triple-sized group, which is named Group 8B in CAS system and Group 8 in old IUPAC system. Furthermore, the old IUPAC system uses 0 instead of numerals from 1 to 8 for the noble gases group and considers it as the group 0. Since CAS and old IUPAC systems in most cases use same names for different groups, resulting in confusion, the modern IUPAC group number system was developed to replace them. As it was mentioned before, the periodic table provides us with a very useful framework for studying properties of elements and their compounds, and notably periodicity or recurring pattern of properties. As an example, we can have a brief look at second and third periods and their alkali metals, lithium and sodium. Period 2 starts with the element lithium, which is the most reactive metal of the second period. Then across the period, from left to right, metallic behavior decreases while non-metallic behavior increases, reaching the maximum at the element fluorine as the most reactive non-metal. Finally, the second period ends with the element neon, an inert noble gas. The same trend is observed in the period 3, which starts with the element sodium, the most reactive metal of the third period, and ends with the elements chlorine and argon, where chlorine is the most reactive non-metal of the third period and argon is an inert noble gas. As such, recurring pattern also suggests both lithium and sodium, which belong to the same alkali metals group, are highly reactive metals sharing similarities in their properties, like easily reacting with water to lose one electron per atom and form +1 cations. The trends like changing from metallic behavior to non-metallic behavior across periods and similarities in properties of same group elements are not local or specific to certain places of the periodic table like second and third periods or alkali metals group. In fact, such trends can be considered more or less as the general trends of the periodic table, although there may exist exceptions to applicability of these general trends. For example, we can talk of the general trend of changing from metallic behavior to non-metallic behavior across periods from left to right. With this fact in mind, that not all cases may obey this general trend as smoothly as we may expect. For instance, there is no metal in the period 1, while metals of the 6th period extend up to groups 15 and 16 well near the rightmost side of the periodic table. As another example, elements of a same group generally have similar properties different from properties of elements of other groups. However, similarities between properties of nearby elements of a same period can also be considerable, as in the case of the D block elements, or more profoundly, the F block elements, lanthanoids and actinoids. The underlying reason for such general trends in the periodic table is the fact that the arrangement of the periodic table is based on electronic configuration of elements, which is also the main contributor to the determination of properties of elements. Any similarities or differences in properties of elements can ultimately be linked to their electronic configurations, and the recurring pattern in the electronic configuration of elements when listed in the order of increasing atomic number is the cause of recurring pattern or periodicity of properties of elements or the associated general trends. Our modern theories, backed by innovative experiments, can well explain these recurring patterns, thanks to the theoretical or experimental contributions by many great scientists. Mendeleev and scientists of his era were unaware of electronic configuration or even atomic number, but they were keen to notice similarities in properties of groups of elements. And with the log from correlation between atomic number and atomic weight, they were able to give rise to initial periodic tables and proposal of the periodic law. At the end, it should be noted that there are many proposed formats for the periodic table. And besides two-dimensional rectangular forms like the one represented here, other two-dimensional and also three-dimensional alternatives using shapes like circle, spiral, and pyramid are devised. The one represented here is based on IUPAC periodic table of the elements dated 1 December 2018. For the original IUPAC periodic table of the elements and also for notes and updates to it, see www.iupac.org.